Hey everybody, I'm going to do an example here of creating, well, you can see a vector function. Sorry, my writing is a little messy. I'm still not perfect with this thing. So I want to find a vector function for the space curve defined by the intersection of two surfaces. So my surfaces are x squared plus y squared equals 4, and then x plus 2z equals 2, okay? And so, we have to imagine this thing, and if you remember, x squared plus y squared equals 4, since z doesn't show up, this is an easy one to think about. X squared plus y squared equals 4, if we were in 2 dimensions, would be a circle with radius 2, centered at the origin. So all the points of this surface have to have xy coordinates that above and below that circle in the xy plane, and then the z coordinate doesn't matter. So it's going to be a cylinder extending around the z-axis. And then this is just a plane. So I actually have these graphs. Let's take a look. So the red is the cylinder, obviously, and then this blue plane. And we can see their intersection, right? From above, it looks like a circle. Well, it doesn't show us that. Actually, I can make it show it. So from above, it's a circle, this intersection. I put a little black line on the intersection, but it's at an angle, okay? So we have to figure out how we can create that vector function. So what we need is something that's going to spit out coordinates on that intersection, okay? And keep in mind, what I said is that we're going to find a vector function. The process is equivalent to finding a set of parametric equations that are going to spit out the points, right? Those two things are interlocked. So when we have a vector function, there's an associated space curve, and then in the space curve, there's an associated vector function. So what we're going to do, we're going to start with this piece of the puzzle. Since we know every point in our vector function lives on this circle, so remember this is a circle in the xy plane, so I'm just sort of ignoring the z information for a moment, and it's got a center at the origin and a radius of 2. Well, we've seen how to parameterize that. We can make our x coordinate equal to 2 cosine, I'll use t as our parameter, and y will be 2 sine of t, right? So if you look back to the first video on parameterization, or maybe the second one, we did a parameterization of a circle. I don't think we had a 2 here. We had just cosine and sine, and we had a circle radius 1. If we just extend everything, double everything, we're going to get a circle of radius 2. So if I make my x and y coordinates in this parameterization, it ensures that they live somewhere on this red cylinder, right? Now the key is making sure that the z coordinate is correct, right? So I don't want, for instance, where I'm marking right now, let's make it black, right? There's a point up here, right? That's on that surface, but it's not in the plane, and so it's not part of the surface we actually want. So we have to do some other work to make sure that that's the case. So let's try to do that. So what we need to now do is just incorporate the fact that this surface lives on this plane. X plus 2z equals 2. So as long as we hold this relationship true, then we have to live on that plane, right? So we've already ensured that the first relationship is true. Every x and y coordinate, if you square them and add them together, you'll get 4. Now we need to have this relationship between x plus 2z equals 2. So we need this relationship encoded. Well, this is pretty simple to do. If I solve this equation for z, I get z equals, so it'll be 1/2 2 minus x, right? But I know what x is in terms of my parameter t. X we just decided was 2 cosine of t. I can now simplify this equation. This is 1 minus cosine of t. Okay, so let's review. Well, let me write it all out and then we'll review. This gives me the vector function 2 cosine of t, 2 sine of t, and 1 minus cosine of t, right? Or the associated space curve with parametric equations 2 cosine of t, y equals 2 sine of t, and z equals 1 minus cosine of t. And if we wanted this to just go around this curve once, we could insist, for instance, that t be between 0 and 2 pi. Any 2 pi interval will work. Negative pi to pi would work. 17 pi to 19 pi would also work. And that will give us, these are the parameterizations of the space curve. I'll call it the curve C, and then this is the associated vector function. Remember the vector function, right? If this is my space curve C, my vector function we can think of as pointing at points along that curve. Later on, if I put in a different t value, it's going to point at a different point along that curve, right? So that's what our vector functions do. If we go back to, oops, this graph, let's get rid of this. This is exactly the function that I put in. Let me erase all this. Right, so if you look closely on the left-hand side of the screen, you can see the function over here is exactly as I said, right? 2 cosine, 2 sine, 1 minus cosine t. This is the parameterization. So the software spits out all those points. That's what this black line is. That helped me visualize for you what the intersection is. That's just the plane and the cylinder, and I put that in. We've got our space curve along that intersection. Okay, that is it for this one. Thanks, everybody. I'll see you next time. Oops, let me actually stop.